Hidden inside your body, a tiny circuit just stitched itself back together. No doctors, no surgery, no scar. This is the secret behind the world's first living electronics. South Korean scientists may have just changed the future of medicine with a material so advanced it bleeds, heals, and survives like human tissue. While there's no denying that it's the beginning of something entirely new, the question is, are we ready for machines that heal like us and live inside us? Machines that don't heal. If we're being honest, it's easy to forget just how fragile the machines inside us really are. Pacemakers, cochlear implants, spinal cord stimulators, these devices have transformed millions of lives. But they all share one serious flaw. They're rigid, they wear out. And when they break, they don't heal. They get replaced. That means more surgeries, more scar tissue, more risk, especially for people who depend on these devices to breathe, hear, walk, or stay alive. But what if the electronics in your body could stretch, flex, and even heal like skin? First things first, they'll need to be soft because your heart doesn't beat in a straight line. They need to be stretchable because your lungs expand and collapse with every breath. And above all, they need to be biocompatible. They have to work with your tissues, not against them. It's a massive engineering challenge. How do you make something as smart as a circuit behave as naturally as living flesh? Up until now, most attempts have either been too stiff, too fragile, or just too unstable inside the body. But that might be changing. South Korea's breakthrough in living electronics. In labs across Asia, Europe, and North America, materials are emerging that bend, flex, and recover without needing external power or human intervention. And in 2025, a team of South Korean researchers working out of Sungkyunkwan University and the Institute for Basic Science may have finally cracked the code. They've built something the world has never seen before. A fully functional self-healing electronic circuit designed to live inside the human body. It's not just another medical device. It's the first step toward electronics that aren't just implanted, they're integrated. And that changes everything. This group of scientists didn't just make a single sensor or a one-off prototype. They built a complete, working transistor with every critical layer made from materials that can heal themselves. And they didn't stop at one. This was the first scalable method for building full integrated circuits, meaning not just the semiconductor, but also the dielectric, the electrodes, the whole thing. All of it self-repairing, all of it stretchable. Published in Nature Electronics, this breakthrough quietly signaled a new phase in medical technology. For the first time, we had circuitry that could be damaged, torn, twisted, and still come back to life. No soldering, no replacement, no external help. Materials and mechanisms of self-healing circuits. For context, let's zoom in on what that actually means. Most modern electronics are built like layered cakes, thin films, stacked precisely, each with a different role. The semiconductor is where switching happens. The dielectric controls the switching, and the electrodes move the charge in and out. In traditional systems, even minor damage to any one of these layers means failure. There's no redundancy. You don't patch a logic gate with duct tape. But in this new Korean system, each of those layers was engineered with self-healing functionality. If the dielectric layer cracked, it flowed back together. If the electrode snapped, it reconnected its own path. Even the semiconductor, historically the most brittle and sensitive of the bunch, was made with a special blend of organic molecules and stretchable polymers that reformed their structure after being cut. And this didn't just happen in theory, it worked in practice. In the lab, researchers would bend a logic circuit until the connections visibly broke. The signal dropped. Functionality stopped. Then, the material would do what human tissue does. It would reconnect, almost like a blood vessel closing after a wound. A few seconds later, the signal came back. The gate worked again. The circuit wasn't replaced. It was reborn. What makes this truly groundbreaking isn't just the chemistry, it's the scalability. This wasn't one transistor performing a clever trick. It was an entire circuit architecture, repeatable, reproducible, and built using methods that could potentially be scaled for commercial production. The implications are enormous, because now, for the first time, we can build electronic systems that don't just survive inside the human body. They live there, not in sterile, sealed capsules, but out in the open, flexing, bending, stretching, and healing, alongside the very organs they're designed to support. It's a shift from machines that fail to machines that adapt, and that opens the door to a future where your electronics don't just monitor your health. They recover with you. Logic and computation in flexible bioelectronics. So how does this actually happen? How does an electronic circuit, something we usually think of as fragile and rigid suddenly behave more like living tissue? It all comes down to the materials. These circuits aren't made from traditional silicon. They're built from a blend of organic semiconductors and self-healing polymers, carefully engineered to do something wild: flow, reconnect, and restore themselves automatically when damaged. At the heart of it is a class of polymers that scientists refer to as dynamic or reversible. Think of them like a net made of Velcro. When the net is torn, the loose strands aren't permanently broken, they're just temporarily separated. Under the right conditions, they snap back into place. That's what's happening here, except on a microscopic scale. Let's say a circuit is stretched too far. The conductive pathways inside might snap. Normally, that's the end of the road. The charge has nowhere to go. But in these materials, the tear triggers a chemical response. Microcapsules rupture, releasing a healing agent that spreads into the damaged area and restores the broken links. This process happens without heat, without electricity, and without any external intervention. It's completely passive. And that's key, because inside the human body, you can't call a repair technician. These devices have to look after themselves. But it's not just about sealing the wound. These materials also need to maintain their electrical properties. It's one thing to glue a crack shut, it's another to make sure electrons can still flow through that crack once it's healed. In tests, the researchers found that their circuits could restore conductivity to nearly original levels, even after repeated damage. After one cycle of tearing and healing, the electrical performance recovered almost entirely. After 5 cycles, still working. And they were not just sitting idle. They were under mechanical strain, bent, stretched, twisted, and pushed to their limits in ways that simulate real conditions inside the human body. That's a brutal test. Think of something like a heart patch or a stomach monitor. These organs don't move in a predictable linear way. They pulse, they stretch unevenly, they twist, they contract in rhythms. Electronics inside them have to handle that chaos day after day. Most materials break down swiftly under those conditions. These new circuits don't. They adapt, they reform, they heal. It's the first time we've seen electronics begin to approach the resilience of biology, not in theory, but in functional, testable, lab-verified systems. And that changes the rules for what we can implant in the body, and trust to stay there for the long haul. It's one thing to make a wire reconnect or a sensor regain its signal, but logic? Logic is the heart of computation. The moment you start talking about gates and/or and nor, you're not just building a gadget anymore, you're building a brain. That's what makes this next part so extraordinary. Because the team didn't stop at proving self-healing in isolated components, they pushed the idea all the way into functional logic circuits. Entire systems made from parts that could be cut, stretched, torn, and still compute. They built a series of logic gates that could process inputs and generate outputs, just like the ones in your phone or computer. Except these weren't protected inside a metal shell. They were printed onto flexible substrates, thin, transparent, bendable, and tested under mechanical stress. And still, they work. Real-world organ applications and tests. Let's break it down. The researchers constructed or and NOR gates using organic transistors layered with their new self-healing materials. These gates could respond to voltage signals like any basic logic circuit should. When voltage was applied to the inputs, the correct output was produced. Nothing unusual until they broke it. Literally. They cut through the circuits, disrupted the layers, ruptured the connections. Immediately, the signal dropped. The logic gate failed. But then something remarkable happened. The materials healed. The microcapsules leaked their conductive fluid. The polymers began to flow. And within moments, the gate was back. Same inputs, same outputs, logic restored. This wasn't just repair, it was functional resurrection. The kind of thing we've never seen before in fully integrated electronics. And it didn't end with logic. They also built early-stage active matrix displays, thin, flexible panels with light-emitting pixels connected through self-healing lines. Those displays were damaged too, bent, ripped, scratched. Then, healed. The pixels lit back up. The signals flowed. It wasn't flawless, but it was proof. Proof that a display could come back online on its own. Think about that. A wearable device, a soft implant, a patch on the skin or organ surface, it could show feedback, display data, blink a warning, then recover if injured. And that's what makes this system so powerful. We're not just talking about sensors that read your body and send the info somewhere else. We're talking about autonomous systems, devices that can sense, process, and even display, all while moving with you, and all capable of healing themselves on demand. In traditional medical implants, the moment something breaks, The entire system becomes a risk. A loose wire, a failed logic unit. That's a second surgery, a battery drain, an infection risk. But with a system like this, you could implant a device once and it could last for years. Not because it's indestructible, but because it knows how to recover. Roadmap, from prototype to clinical use. Imagine a neural interface that stays sharp after hundreds of micro movements inside the brain. A cardiac monitor that keeps analyzing arrhythmias, even after getting jolted or flexed by a chest impact. Or a stretchable diagnostic patch that displays warnings directly on the skin, then stitches its own circuits back together while you sleep. These aren't science fiction stories. Although you can find this technology shown on the Apple TV show Foundation. The prototypes are real. They've been tested, broken, healed, and tested again. The logic circuits in particular represent a huge leap, because computation is where things usually fall apart. Even the smallest interruption can throw off a decision-making chain. That's why integrated logic is usually the last thing to go, soft or flexible. It's too fragile, too precise. But this breakthrough changes that equation. It says we can build logic that bends, logic that adapts, logic that doesn't quit just because it got injured. It's not just about durability anymore. It's about intelligence that heals. Okay, so we've seen the science, we've seen the materials, we've even seen the logic. But let's bring it home. Let's talk about what this tech could actually do for people. Because the team behind these self-healing circuits wasn't just building for the lab, they were building for the human body. And the body is not an easy environment. It flexes in unpredictable ways. And it doesn't particularly like foreign objects. Traditional electronics, like the kind used in pacemakers or neural implants, need to be sealed in titanium or wrapped in rigid, biocompatible shells just to survive inside us. And even then, they break down over time. Wires snap, insulation cracks, batteries swell, and every time one of those things fails, it means risk. Risk of malfunction, risk of infection, risk of going under the knife again. So now imagine the excitement of an implant that doesn't fail when it's bent. That doesn't short out if it gets tugged or stretched. That can literally heal itself after injury while still inside your body. That's the promise of this new technology. The researchers didn't just test their self-healing circuits on static platforms. They tested them in conditions that simulate real, moving organs. One of the most eye-opening demonstrations? A stretchable sensor patch designed for the human bladder. This test was so important because the bladder is a perfect stress test. It expands dramatically when it fills with fluid, sometimes up to 5 times its resting volume. Then it contracts, and it does that cycle over and over every single day. That kind of movement destroys traditional electronics. So the team took their new self-healing conductive patch, thin, soft, and elastic, and applied it to a bladder model that could expand and contract repeatedly. The circuit had to stretch with the tissue, maintain conductivity, and then recover if it was damaged. And it passed. Even after aggressive mechanical stress, pulling, twisting, overextension, the patch healed itself and kept transmitting signals. It didn't need surgical repair. It didn't stop functioning. It just bounced back. Now imagine what that means. Patients with overactive bladder, people with spinal injuries, who've lost full bladder control. Cancer survivors, who've had parts of their bladder reconstructed. Instead of relying on external catheters or intrusive mechanical sensors, they could one day wear a flexible internal patch, a one that monitors pressure, activity, or urgency, and heals itself for years without replacement. But the bladder is just one organ. This tech could go further. Cardiac patches that stretch with every heartbeat, sensing irregular rhythms and healing microtears on their own. Vagus nerve stimulators that monitor and regulate inflammation, epilepsy, even depression, and stay functional through hundreds of bending cycles along the neck and chest. Brain implants that track seizures, interface with prosthetics, or help restore sensory input without needing rigid probes that scar surrounding tissue. Because here's the thing, most of the body's vital systems move, constantly, and every movement puts stress on rigid implants. That stress leads to damage. That damage leads to failure. But if the implant moves with the body, if it flexes and heals like the tissue around it, then we're talking about a new category of bioelectronics. Not just wearable, not just implantable, truly integrated. It's a leap toward long-term, low-risk biointerfaces, the kind of implants you put in once and forget about for years. Devices that don't fail just because life happened. And for patients, that means fewer surgeries, less monitoring, more trust. Trust that your implant will keep working through exercise, accidents, aging. Trust that it's not going to quit on you when you need it most. Of course, we're still early. These circuits aren't yet inside people. There are hurdles ahead: mass production, miniaturization, long-term biocompatibility studies. But the science works. The foundation is real. We now know it's possible to build an entire circuit, logic, sensors, even displays that's flexible, stretchable, and fully self-healing. And we've seen that those circuits can function in environments that mimic the complexity of the human body. This isn't a lab project, it's the beginning of a medical revolution. Because if your body can heal, shouldn't your electronics be able to heal too? Future implications, ethics, and next steps. We're entering an era where the line between biology and electronics is starting to blur. Circuits that can bend like skin, transistors that can stitch themselves back together, patches that can flex with your heartbeat, stretch with your muscles, and heal from damage, just like living tissue. This isn't the future of electronics, it's the beginning of living electronics. Think about what that means. No more ripped wires and pacemakers. No more rigid implants scraping against tissue. No more sensors that break the moment life gets messy. Instead, we're talking about devices that live with the body, that survive failure, that can adapt, recover, and keep going just like us. South Korea's breakthrough isn't just another research paper, it's a signal. A glimpse at a world where our medical technology becomes as resilient as the people it's meant to help. And that raises a big question. If machines can now repair themselves, how long before your body has backup systems smarter than you? Let that sink in. If you found this fascinating, hit that like button. It helps more people find this video. And if you want more cutting-edge tech explained like this, subscribe and turn on notifications. We've got a lot more coming. In the comments, tell us, would you trust a self-healing implant inside your body? Thanks for watching. Stay blessed and stay curious.